Standard AI prompts hit a centralized node and scatter. When an employee uploads a proprietary document to a centralized provider, that data is logged, stored, and exposed to the provider's infrastructure. Samsung and Amazon have already faced significant internal source code and document leaks through these default plaintext channels. Systems architecture defines privacy across a 5-tier structural spectrum. Level 0 sits at the bottom with total plaintext exposure, while Level 4 at the top represents complete physical isolation. Every project markets itself as private, but the actual security guarantee depends on the specific hardware and cryptographic boundaries in place. Independent research from the decentralized AI infrastructure platform Own Your Mind reveals how widely these architectural definitions vary in production. The Venice platform serves as a functional model for this complexity. A single consumer application can offer 4 distinctly different mechanical definitions of inference privacy, depending on the user's selected mode. To identify exactly where data leaks occur, we have to trace the path of a prompt. We will follow a single query from a local device through the network routing layer and directly into GPU memory across all 5 levels of the spectrum. Understanding where a platform sits on this ladder is a prerequisite for enterprise deployment. Mapping sensitive data to an insufficient privacy tier represents a fundamental failure in systems architecture. This network flow diagram maps Level 0, no privacy. This is the baseline for default OpenAI and Anthropic accounts. A data packet containing both a user identity badge and a plain text document travels to a central server. The provider sees who sent the request and what it contains, storing both indefinitely on their own infrastructure. Level 1 introduces policy-based privacy, the default mode for Venice, and the routing layer for Morpheus. Here, the data packet hits an intermediary proxy node. The user identity badge is stripped away, but the plain text document continues its journey to the target execution server. This architecture relies on anonymization. When the prompt reaches the distributed GPU provider, the hardware processing the request has no record of who sent it. The link between the user and the data is broken. As we zoom into the target server's GPU, the vulnerability of Level 1 becomes clear. The text document is fully visible and unencrypted inside the GPU memory. To execute inference and generate a response, the compute provider must read the prompt in plaintext. Platforms at this level operate on a zero data retention policy. The provider is contractually obligated not to log the prompt. However, there is no physical or cryptographic mechanism preventing a compromised node from scraping data during the milliseconds it sits in the GPU. The Morpheus network recently hardened this layer with its version 6 update. It introduced proxy-router attestation, which provides cryptographic proof that the routing node is genuine and has chat logging permanently disabled at the build level. Morpheus functions as a decentralized marketplace, verifying these routing nodes. However, it does not control the endpoint GPUs. Even with an attested router, the final execution environment still receives and processes the prompt in plain text. Level 1 effectively hides the who but exposes the what. This makes it sufficient for generic creative work or coding, but structurally unsuited for handling proprietary enterprise intellectual property. Level 2 moves data protection from legal contracts to physical hardware constraints. As this microchip seals itself under an isolated boundary, it demonstrates hardware-enforced privacy. This schematic shows a server utilizing trusted execution environments. A TEE isolates code and data. The host operating system and server administrator are physically blocked from the enclave. An encrypted packet enters, decrypts only inside this hardware boundary to process inference, and re-encrypts before exiting. Venice's end-to-end encryption mode adds another layer by implementing ECDH key exchange and AES-256 GCM encryption on the client side. ECDH allows 2 parties to establish a shared secret, while AES-256 GCM is a high-speed authenticated encryption standard. The prompt is locked before it ever leaves the browser. Because the data is locked on the user's device, the prompt is only decrypted once it reaches the verified hardware enclave. This ensures that neither the application provider nor the physical GPU operator can ever view the plain text content. These systems generate cryptographic attestation reports to prove the hardware is secure. An attestation report is a mathematical statement verifying the enclave is genuine. Engineers use these reports to verify the security of the environment before sending data. This level requires trade-offs. External features like web search must be disabled to prevent data leakage, and the security of the entire system relies on hardware vendors like Intel and NVIDIA correctly implementing the silicon. Level 2 replaces Trust Our Policy with Verify Our Cryptographic Attestation. This allows regulated industries like healthcare and law to utilize cloud AI while maintaining verifiable data protection. Level 3 removes the physical hardware vendor from the trust equation, relying entirely on the pure mathematics of cryptographic privacy. The primary technology here is fully homomorphic encryption, or FHE. FHE allows a computer to perform calculations on scrambled data without ever needing to decrypt it first. In this diagram, a GPU processes a mathematical equation where all variables and outputs are masked by lock icons. The provider receives a scrambled prompt, runs the model on that ciphertext, and produces a scrambled answer. The computation is completed successfully without the data ever being unlocked. The diagram now illustrates multi-party computation, or MPC, used in the RCM architecture. MPC is a protocol that splits a single computation among multiple independent parties. An encrypted packet is fragmented and sent to separate GPU nodes. No single node sees the complete prompt, and the result is only recombined at the user's origin. Enterprise adoption of Level 3 is currently limited by latency. Processing math on encrypted data results in a computational quality of 100 to 1,000 times for FHE and creates massive network overhead for MPC coordination. While Level 3 provides absolute mathematical trust, its performance limitations currently restrict its use to research and batch processing workloads. For strict threat models where no network transmission is acceptable at all, Level 4 offers the final standard of privacy, local inference. This mechanic involves running open-weight models on user-owned hardware. When you run a model like Llama locally on a Mac Studio, the prompt never leaves your physical machine, eliminating the need for a provider entirely. This approach requires high upfront capital expenditure for hardware and limits users to open-weight models, preventing access to closed-weight frontier models hosted in the cloud. Physical isolation remains the gold standard for state secrets and extreme intellectual property sensitivity, where the scale of the cloud is traded for total local control. To maintain efficiency, technical operators must map their AI architecture strictly to their threat models. This 3-column decision matrix highlights the relationship between the workload profile, the threat model, and the required architecture. For general software development and data analysis, Level 1 anonymization is the target. If the primary threat is corporate data scraping, proxy routing provides the necessary protection with no performance cost. The middle row covers regulated data in healthcare, legal, and corporate IP. When the threat model includes a compromised host or a compliance audit, the architecture must utilize Level 2 hardware enclaves for verifiable protection. The bottom row is reserved for extreme sensitivity. If the threat model includes hardware zero-day exploits, operators must use Level 4 air-gapped local hardware to ensure absolute physical assurance. Regulatory pressure from the EU AI Act and HIPAA is already invalidating trust-based privacy policies. In these environments, demonstrating data protection during processing is becoming a baseline requirement for doing business. Decentralized compute networks are currently providing the economic foundation for this shift. By reducing hardware costs, these networks allow providers to offer hardware-attested privacy as a standard feature rather than a premium service. The winning AI infrastructure projects will integrate cryptographic and hardware attestation directly into the compute layer. This move will establish verifiable privacy as the invisible default standard for AI inference.